Hey everyone, this is Professor Iris Miano giving you a lecture video on solving systems of linear equations by one of two methods, substitution or the addition method, also known as elimination method. There's another method actually by which you could solve a system of equations, and that would be by graphing, but I believe we've already covered that in a previous handout where we just graph the line of that represents the two equations in question and just see where they intersect, if indeed they do. So we'll just bypass that method and focus on these two methods here, the first being substitution, the second being the elimination method. Okay, so let's go over the substitution method. Step one, you will solve one of the equations for one of its variables. Now sometimes you'll be given a system that already has one of the equations in that form, so you might have some examples to tackle in which that step one has already been addressed. Step two, you will substitute the expression for the variable you solved in step one. Step three, we will solve this equation to find the value of one of the variables, and then we'll substitute it back into the original system in order for the other variable's value to pop out for us. Okay, let's do a couple of examples in order to just practice this. Oh, of course, getting ahead of myself. Step five, you will check your proposed solution in the original system. Now, in this demonstration here, I do not go through the process of checking my solution, but if you are wondering if your solution actually does work out, you could just plug it back into the system and for both equations, of course, both values that you've solved, and see if they satisfy both of the equations, and if they do, then everything's good to go, and if they don't, well, you might want to go back into your work and try and find your error. All right, here we go. Let's try this first example A here. Notice that we have one of the equations, I'll call it equation 2, and I like to, when I'm dealing with solving systems of equations, label the equations equation 1 and equation 2 accordingly, like with these little circled numbers here. I think it's just easier to, in the process of describing it to you, what the steps are, to just refer to equation 1 rather than say, in this case, 2x plus 3y equals 13, or even the top one, I don't know. If they have clear labels, I feel like it's a little easier to describe what's going on. So notice that equation 2 is already solved for x. So we're going to plug equation 2 into equation 1. I know my little labels here are floating up in space. So apologies if that looks a little jarring, but yes, so what I mean is in equation 1, the place where this x lives, where my cursor is hovering, I'm going to substitute it, completely replace this x with the quantity y plus 4, and I'll do that by putting the y plus 4 in parentheses to completely replace or substitute that x. Okay. So that's like a new way of thinking, a new representation of equation 1, but it still hasn't changed its value according to its collective representation within the system, if that makes sense. Anyway, that's neither here nor there. Now what you're dealing with here is an equation that only has one kind of variable in it. And whenever you have a single equation with only a single unknown in it, you can solve for that unknown. So let's go ahead and bust out the algebra that gets us to the value of y, starting with distributing that 2 over the quantity y plus 4, and we'll get the following here. Combine those y terms, subtract 8 from both sides, and then lastly, divide both sides by 5, and you will get that y is taking on a value of 1. Cool. All right. Take that y equals 1 and plug it into either equation 1 or equation 2 in the original system. It doesn't matter which one you choose. I would choose plugging it into equation 2 because it seems like it's just a simpler equation. It's already set equal to the other variable that I'm now trying to solve for, and like the numbers are just smaller that I'm working with. And by numbers I mean the coefficients and the constant term when comparing it to what you see in equation 1. Could I have plugged into y equals 1 into equation 1 and still gotten the correct final answer for the other variable's value? Of course, but I always want to do whatever I perceive to be as easiest. Fewest number of steps, most straightforward, that's always going to be my go-to methodology that I'll give you. Okay, so plug in y equals 1 into the second equation in the original system, and you will find that x therefore equals 5. So you can write your solution in set notation, it'll be ordered as an ordered pair, as an ordered pair. So you notice that your x value is first, and then you have a comma, and the y value being encapsulated by some parentheses. This is definitely, this is not interval notation. Nope, not at all. This is, it's a very similar notation, but the context here is that we want to present the final answer as an ordered pair. Is it okay for you to have your final answer be x equals 5 and y equals 1 like on your paper? Sure, but when you're in the midst of your completing your online homework or trying to present a final answer for a question like this as it's presented on an exam, you want to just follow their directions, whatever they may be. Now, if they're asking you to present your final answer as an ordered pair, this is what it would look like in the green box. Okay. Moving on, let's have another example here. Again, we'll use the substitution method. Notice that equation 2, as I've just now labeled it, is already solved for y. So it'll be, this system is like designed to have the solution be brought about by the substitution method. Okay, so plug equation 1 into equation 2, just very much similarly like we did into the first example, and you'll get this, right? Instead of this y in equation 1, you're going to substitute it with 5x, because that's what equation 2 said that y's value was, right? Okay, so plug it in, drop the parentheses, combine like terms on those x's, you'll get a negative 1x or just negative x. Multiply both sides by negative 1, and you'll get that x is taking on a value of negative 2 in that half of the solution. Plug that into either equation 1 or equation 2 in the original system. Again, I'm choosing equation 2 because it just seems a bit simpler. And you'll take that negative 2 and multiply it by the 5. That's the coefficient in that particular equation. And then you will recognize that y equals negative 10. So presenting the final answer as an ordered pair, it'll look like this inside of the green box. Okay, cool. Let's do another one. And notice that the as I click forward, the font is getting smaller. That means this example might need a little bit more work, a little bit more steps are going on here. Now, yes, and notice right off the bat that this system is not presented to you, equations 1 and 2, in any sort of way that lends itself necessarily to the substitution method. However, we're still in this section called Solving Systems by Substitution, so we want to, being given this system, how would we go about starting the process of solving it by substitution? Well, I would take equation 1 and I would solve it for y, because it seems like it'd be one step in order to do that. It'd just be subtracting 3x from both sides, and then, poof, it's solved for y, and it looks like so. Okay, now that I have equation 1 solved for y, I'm going to plug that into equation 2. So in equation 2, you see how it's the y value is right here, this variable term, that's where the y is located. Instead of that y, I'm going to plug in the quantity negative 3x plus 5, substitute it in. Y is equal to this expression, so you should be able to plug it into the other equation accordingly. Now, distribute that negative 2 over the quantity, combine like terms, add 10 to both sides, divide both sides by 9, and you will reduce that fraction and you'll get a value of 1/3 for x. Is it okay that x's value at this stage of the game is a fraction? I really would have liked it to be at least an integer. The whole number would have even been better, but you don't always get what you want as far as the value of final answers are concerned. And fractions are certainly acceptable representations for your final answers. So considering that x equals 1/3, all right, let's go ahead and plug that into either equation 1 or 2. I think maybe plugging it into 1 will be a little bit easier, because then the value of y will just kind of pop out naturally. And thank goodness the coefficient on the x term in equation 1 and 2 actually is a 3. So right away, even though our input value is a fraction, we're going to multiply it by its reciprocal. So that way it's going to end up being an integer value of 1 in this case. We'll subtract 1 from both sides and we'll get y equals 4. Okay, so then the ordered pair final answer therefore becomes 1/3, 4. And that'll do it. And if you're, wondering, oh, is this actually legit? Do I feel good about this final answer? You can always plug these values back into both equations in the original system, and they should satisfy the equation. And by that I mean when you plug in those values, you should be able to simplify both sides of the equation and have them equate one another. And that will work. This is the solution. I'm confident in that, but you can check it if you are feeling suspicious of it. Okay. Cool. Let's move on to the next example here. I'm going to choose to, here I go labeling my equations again. I'm going to choose to solve equation 2 for y. And again, I'm doing that because it is a one-step process in order to do that. Whereas if I wanted to solve equation 1 for either y or x, it would take 2 steps and I'd have some weird fractions going on as the coefficients for the variable and constant term on the other side. I don't want to do that. I just want to add 3x to both sides, and that's what it takes in order to solve equation 2 for y. So here we go. Now plug 3x minus 3 into your y position in the first equation, and it'll look like this. Okay, now we do the same thing that we've been doing in the last few examples. Once you have your equation set up for the with the substitution already in place, you can solve that equation for the one variable that it now contains. So go ahead and distribute that -2, combine like terms for the x, subtract 6 from both sides. Oh, we have negative x equals 0. That feels weird, but is it wrong? No, we've done everything right so far. There's no reason why the x value couldn't take on a value of 0. Sure, it could. And you'll want to simplify this all the way down from this step by either multiplying or dividing both sides by -1, and that'll get you where you want to go with that. Final answer, explicitly writing it as x proper, no negative sign or coefficient going on in the x is equal to 0. We're done with that. Okay, so x equals 0. Cool. Go ahead and plug that into either equation 1 or 2. I guess when I was writing this up, I decided to plug it into equation 2. So there you go. Here is a 0 value for x in the original equation 2 in the system. That zeroes out this entire first term, and then I will get y equals -3. So there you have it. The solution for this system is the ordered pair 0, -3. X equals 0, y equals -3. And that's that. Okay, let's have another example here. Let's solve this system, and again we'll use the substitution method for this, and it's tailor-made the way it comes to you, this particular system, for the substitution method, because look, equation 2 is already solved for y, so let's go ahead and plug it into equation 1. So instead of y for equation 1, we're going to replace it with the quantity 1/3 x plus 2. Awesomely, in distributing that 3 as a first step in solving this new equation, we're going to encounter multiplicative inverses. So 3 times 1/3 is going to give us 1x. That's how we get this here. And then the 3 further distributes to the 2, getting the 6 here. Notice what else is happening though. Oh my goodness. In combining like terms on the x's, what's going to happen? Well, those x's are going to cancel each other out. And then you get this really super forehead slappingly obvious equation of 6 equals 6. Well, of course 6 equals 6, right? It's just, what's happening here? Well, when your variables completely cancel out and you're left with a true statement like this, 6 equals 6, 5 equals 5, 1,000 equals 1,000, or something like that, you could actually go a step further and subtract that constant term from both sides and get 0 equals 0. Or if you get anything equals itself, then you know that you have encountered a system that has infinitely many solutions. And the way that you present those infinitely many solutions is by busting out some set builder notation. So curly brackets, you need to figure out how to effectively write the name of the set of values inside of these curly brackets or braces. So the way that this statement reads here that you just see popped up on the screen is the set of all x and y values such that they are governed by the equation -x plus 3y equals 6. Something of that nature. So why did I pick equation 1, the -x plus 3y equals 6? No reason. I could have easily presented the final answer with set builder notation, grabbing equation 2. That's just as correct. It's like when you have this particular type of situation, it's like these two equations are they lay right on top of each other if you were to graph them in a coordinate plane. So they're the same thing. And you want to grab all x and y values that satisfy either of these equations because they are literally the same. They don't look the same, right? Because, you know, one of them is solved for y and the other isn't, but they're equivalent to one another. And so all of the x and y pairs that are present on the line that is both of them at the same time, those are the infinitely many values that could satisfy this system. Okay, cool. Let me know if you have any more questions about that type of problem or when this is the solution that you get. Okay, cool. Let's do another example here. We're going to have to solve one of these equations for x or y. Let's see what I chose to do. So here's me labeling equations 1 and 2. I decided to solve equation 1 for x. Okay, so that means I'm going to add 3y to both sides and then divide by 2, and then I will get the following. Okay, yes, there's a fraction involved. Don't let that scare you. But do go ahead and plug that new version of equation 1 into equation 2, and it'll look like this. Okay, so once you distribute that -4 over this quantity, the fraction's going to go away because that 4 is going to cancel out with this 2. We won't have denominators to worry about at all. So let me go ahead and do that distribution, and we'll get the following here. Now we would want to combine like terms for the y terms. Notice that they cancel each other out. But then what's left? You are left with -12 equals 5. But is -12 equal to 5? No, as you can see, I've preemptively already put a slashy in there. I'm like, nope, that's not cool. What we've come across here in the process of trying to find the solution for the value of y is an impossibility, a contradiction. Okay, and whenever you come across this, where you have some number is equal to some other number, and you know that that's not right, you can say that this system has no solution. Okay, and you can represent that with the phrasing no solution. You could put a circle with a slash through it, which is just a mathematical shorthand for the empty set, or you could use the set builder notation. I don't have it pictured on the screen here, but you could use curly braces that just have nothing inside of them. That also represents the empty set of solutions as well. Okay, so what's happening here, if you were thinking about this graphically, if you were to graph these two equations on the same coordinate plane, they would be parallel to them. And if you recall the definition of parallel lines, it is two lines that will never cross, okay? And if lines never cross in a coordinate plane, then they represent a system of equations that has no solution. Okay, cool. So that's all the examples that I have of solving systems of equations by getting ahead of myself. Hold on here, guys. By the substitution method. And now here is a series of examples that I have for using the elimination method, also called the addition method. Okay, so same result is, is what we're gunning for here. We're trying to solve the system, but we're going to use a different method. Here we go. So first, let's go through the method. And sorry, it starts off on one line and goes on the other. But the first step is that we want to write each equation in standard form, which is to say that we want to have the x and y terms on the left-hand side of the equation, the constant term on the right-hand side for both equations in the system if it's not already presented that way. You might have instances, depending on how you're given the system, you might be able to skip step 1. Step 2 is to choose a variable to eliminate and then create opposite coefficients for that variable via MPO. Now, I'm not sure if I've done a good job of presenting you guys with the acronym MPO, APO, SPO, or DPO, but they stand for properties of equality. The MPO acronym literally translates to multiplication property of equality, which just means that when you have an equation, you can multiply anything you want by that equation so long as it's the same value multiplied on both sides. You have to maintain that balance that is evident in an equation. Okay, step 3, we want to add the equations together. That's why it's often called the addition method. And then step 4, we solve the resulting equation for the variable you didn't eliminate, and then plug that value into either original equation to solve for the eliminated variable. And then, of course, step 6 is always, or whatever the last step is, whatever number it is, always check your work. You can always plug those values back into your original system to verify that they are correct. Okay, let's jump right in. Notice that the system that we are solving in example A here right off the bat Both equations 1 and 2 are already in standard form. The x's and y's are on the left-hand side of the equation and the constant terms are on the right. So we're ready to roll. Furthermore, notice that the y terms in both equations are opposites of one another straight away. So we can go straight to adding the two equations together. So you want to, of course, make sure that your like terms are lined up and go for it. The y's are going to cancel out because they are additive inverses of one another. So I have kind of an offset slash a little bit. It could have been brought down. Oh well. You guys get the picture though. I'm slashing away those terms and I'm going to get 2x equals what? 18? Yep. So then this resulting equation, you're going to solve it by dividing both sides by 2 and you'll get that x is equal to 9. Great. Take that value of x equals 9, plug it into either equation 1 or 2. I think I chose 2 because the numbers are smaller. When x equals 9, then the value of y becomes 4 ultimately. So then your solution would therefore be the ordered pair 9, 4, x equals 9, y equals 4, ordered pair representation there in dark blue box. Okay, great. Let's have some more examples. Here's another one. Notice again that the system of equations 1 and 2, as I've just now labeled them, are already in standard form. So we don't need to do any manipulation of the system before we get started. However, as far as like getting it in the right form, we do, however, need to choose which variable we want to eliminate. We can either eliminate x by multiplying both sides of equation 2 by 2, or we could decide to eliminate y by multiplying both sides of equation 1 by 4. Do you guys see how there's two different choices here? Neither of them is better than the other one. Whichever one you see as being the next logical step is the correct one to do, I guess. Like, it's all subjective as long as, you know, there are multiple ways to get to the end result here. Like, no one way is going to be better than another one. It's all according to like your feelings about it. Personally, I decided to eliminate x. So I'm going to choose to multiply both sides of equation 2 by 2 and then add the equations together. So here's what that'll look like. So notice every single term on both sides of the equation in equation 2 got multiplied by 2, and that's why we have this new equation 2. It's equivalent to equation 2. It's still equation 2. It just has a little bit of a different look to it, and we've manipulated it in a very specific way because we wanted to eliminate x. Okay? So let's add. Those two terms slash away, and we're left with 7y equals 28. Divide both sides by 7, we'll get y equals 4. Cute. Okay, so put that in your back pocket and plug it into equation 1 or 2. Doesn't matter. I chose to plug it into equation 1, though. And then we will add 4 to both sides. Divide both sides by 2, we'll get x equals 1. So then the ordered pair solution will become a negative 1, 4. And sorry that's cutting off on the bottom of the screen there. I'm not sure. I wasn't able to figure out how to fix like the positioning on that. So yes, the ordered pair solution is negative 1, 4. That's what I'm trying to represent there. It's a little low though. Okay, next example. Let's notice that if there's no best choice, I would say, if you're gonna try and eliminate x or y, it looks like you would do so by multiplying equation 1 by 3 either way. So let's go ahead and do that. I guess I'm explicitly choosing to eliminate x, so I'll multiply equation 1 by 3. And then, but what do you notice happens here? Both the x terms and the y terms cancel out. And we'll get 0 on the left-hand side, but then negative 1 on the right-hand side. Yikes, those do not equate. So it looks like we have reached a contradiction here. What do we do when we reach a contradiction in trying to find the system of equations solution? That means we have no solution. And you can represent that with an empty set, you know, the little 0 with the slashy in it, or just use the phrasing no solution as I've done here. Okay, great. Moving on to the next example. Let's go ahead and choose to, I don't know, eliminate x or y by multiplying equation 1 by 2. All right, what you're going to find though is that it's going to eliminate both x and y, and the constant terms eliminate. So we have that whole scenario in which we have everything cancels out, but we have a true statement resulting, okay? When this happens, we have infinitely many solutions, and we represent the infinitely many solutions using the set builder notation. It doesn't matter which equation you choose, just make sure that you choose one of them for the original system in order to populate the area after your such that bar. So again, if I wanted to read the solution set like how you would say it in English, I'll demonstrate that for this first one where my cursor is hovering. You would say the set of all xy values such that they are governed by the equation 2x plus 5y equals 1. That's not the only way to describe the set builder notation solution set, but that's one way to do it. Okay, and again, it doesn't matter if you choose equation 1 or equation 2 as the equation that governs your solution set. Just pick one and box it up and call it good. All right, here's another example. All right, now it's not obvious which, well, it's kind of obvious, I guess. Here's equations 1 and 2, right? I'm going to choose to eliminate y. I mean, 2 and 5 don't contain any factors of one another, so, I'll have to multiply values to both sides of both equations in order to get them to be opposites, but they already have opposite signs, so I feel like half the battle is already there. So I'm going to multiply equation 1 by positive 2, equation 1 by positive 2 and equation 2 by positive 5. And then I will have the following. And once I've done that, so that's some work, and it'll take a few minutes to figure out all the arithmetic with that. But then once you have it set up, you are nicely being able to slash away the y terms there, and you will be left with 23x equals 23. Cute. So we'll divide both sides by 23 and we'll get x equals 1. Cool. Go ahead and plug that back into either one of the equations in the system. I guess I chose equation 2. Numbers are smaller. It's my go-to, criterion there. So then simplify it all the way down, solve for y, and you get y equals 2. So the ordered pair solution here is 1, 2. Super cute and very basic. Okay, the solution set, I mean. It's just like the ordered pair 1, 2. It just sounds so adorable. Anyway, great. Moving on, another example. Ooh, this one's fun because it is littered with fractions. Oh boy, we've got a lot going on here. So how do we want to tackle this? I would think that it might be best to just clear both equations of their fractions. I see a lot of fractions running around. Each equation has its own LCD, so if I just multiply both sides by that LCD for each individual equation, I'm going to be looking at a system that's way easier to deal with, and it'll be easier for me to decide which variable I want to eliminate. Okay, so I'm going to multiply equation 1, both sides, by 3 to get rid of its denominators, and equation 2 I will multiply by 2, and here will be the resulting system at that point. And then check this out. In doing so, in eliminating the fractions, just to take a more easy look at what is left, the x's are primed to eliminate themselves at this point. Okay, so let's go ahead and cross them out. Add the equations together. We will get negative 2y equals 3. Okay, divide both sides by negative 2 and you get y equals negative 3 halves. That feels a little weird because it's a fraction and it's negative, but it's perfectly fine. We haven't made any errors. So just go ahead and plug that into equation 1. And the original form of equation 1 is what I went with. If you wanted to plug it into this form of equation 1 after multiplying both sides by the LCD, that's perfectly fine as well. I opted for the original equation though, and I noticed that I have an LCD in this case of 6. So I multiply both sides by 6 in order to get this resulting equation. I am leaving out a bit of algebra here. So if there's any of this particular example you guys would like to see me do in class, please by all means ask. I would love to fill in some of the algebraic gaps from this step to this step. I multiply both sides by 6 in order to get from this equation to this one. Okay, so hopefully that is good and makes sense. And if it doesn't, I'll demonstrate more. But for now, let's go ahead and add 9 to both sides, divide both sides by negative 2, and you will get x's negative 17 halves. Yikes, another negative fraction. So yes, the bottom of the screen kind of cuts this off. Sorry about that, but the solution set ordered pair is negative 17 halves. That's your x value, comma, negative 3 halves. Cool. And that's a wrap on those two methods. I hope that's helpful in your endeavor to practice solving systems of linear equations in two variables. Thanks so much for your attention, and I'll see you again soon.